Thank you for the opportunity to speak about HPC here to this crowd. HPC has become more and more dependent on optics to the extent that we're actually engaged in optics in a way that we haven't been before, where we're really trying to drive some of the technology so that it can actually meet some of the needs. So what I want to cover today, I'm going to give you a bit of a flavor of where supercomputers are used in HPC today, and then I want to talk about some of the trends in high-performance computing from a market perspective. I think there's some interesting observations there. Then I'm going to take you a little bit out of your comfort zone, and we're going to transition in talking a little bit about the technical challenges that we see as we move forward in HPC. And then I'll finish with, I'll talk about some of the optics implications at that point, and then I'll try and get into some specifics about what we think we need to do with optics in future systems. So this is a bit of a flavor of what we want to do. So the key thing here, I think, to keep in mind is, and I'll motivate this when I go through the more market segment here, is that HPC is really a complementing experiment these days. And there's an enormous transition from experiment into simulation in many, many areas. And because the cost of computing is dropping at such an enormous rate, this is a very dynamic effect that is accelerating as we go forward. The cost of experiment in some areas is dropping dramatically, but in most areas it's relatively flat or improving slightly, but the cost of computing is truly exponentially dropping, and that really changes the whole environment and opportunities for HPC. But to keep on that curve, there's some enormous challenges, and I'll be taking you through where we view optics is going to have to come in and sort of save the day for us, because without it, we just won't be able to continue to build systems. So let me start with a little bit of a survey. So one of the things that we've done, we have a supercomputer at IBM, one of the ones that we designed. It was one of the world's fastest about 5 years ago, which means it's now about 1/50th of the world's fastest. But in any case, over those 5 years, we've done a lot of applications. We actually made a very large application team focusing on using the machine for real science. So one of the things that we've done, and this was in the New York Times, I wanted to show you here, is trying to actually sequence a genome and trying to hit that where we could actually get to get that step towards personalized medicine. But a lot of this comes down to cost. In the end, these things all end up coming down to cost. And so we're trying to be able to find the structure that allows us to sequence a genome for as much as $100. So this is a movie that shows a simulation that we did, and the green in the center there is an oxygen. You see it's moving to the right. The yellow along the top and bottom are the electrodes here. This is a piece of silicon. It's actually turned sideways, if you like. The silicon is going from, so this top surface is on the left, bottom surface on the right, and as we're pulling a single strand, so this is like half the double helix, it gets pushed through as you apply different voltages on those yellow electrodes, which are different metal layers in the semiconductor. So it's about 4 nanometers vertical here. And you can see it moving along, and what you see floating around there are some ions, and those ions help conduct. And all of this is done in oxygen. There's about 100,000 atoms here. Those are all atoms that you're seeing there. There's about 100,000 atoms that are in this simulation. So those ions are actually used to conduct the electricity. They're important because the way that we sequence this is you actually measure the conductivity as it gets pulled along. You can see it moves in segments. You can see it kind of moves in steps. And it's held by the voltages, and then you cycle the voltages and you let it move along a little bit, and you can see that in this movie. And so that allows us to sort of measure the conductivity at each of those steps, and that's how we do the sequencing. So there's a lot of things that were learned from this. For example, one of the things you can imagine with these ions, there's a screening effect, and to determine the amount of screening is a very complex question. And so from one of the things that they've learned from this is that the screening was about twice as much as originally hypothesized. So this is just one example of the type of things that are done. So let me do a brief survey. I'm not going to go into these in a lot of detail, but let me just touch on a few of them. So the first one here, the phase change in materials, one of the things that we use these supercomputers for is to actually help us design better computers in the future. And one of the huge challenges for the future, and I'll show you a slide on it, is that memory in systems is just not advancing from a cost perspective at the same rate as compute. And so we really need new memory technologies for the future. So there's a lot of fundamental sort of molecular dynamics type of calculations that are done. There are a couple other examples here, similarly, desalination membranes, the photovoltaic materials. These are obviously you recognize as important for sort of as time goes on for the society as a whole. The Blue Gene itself got its name from Gene, which was originally a machine that was supposed to fold a protein, and that's the upper left here. And there's many other biology type calculations that we've done with the machines. I won't go into this, but there's a sort of a sampling here. Other areas that these machines are used for in so EM simulations, electromagnetic simulation, trying to understand the interactions when you get very complicated electronic structures requires really three-dimensional simulations these days, and so it takes an enormous amount of computing. On the right hand, the upper right hand, you see an interesting one. So that's really the simulation of the dropping of a cell phone in this case. So it's really to see what happens when you drop something and how it breaks. You may have noticed when you drop your cell phone, sometimes it doesn't break. Well, that wasn't an accident. There's enormous amounts of engineering that go into that. A lot of it's done experimentally, of course, but when computing gets less expensive, some of these things start to become more attractive to be done through simulation. So that's an example of sort of an emerging area where we see more and more work going on in high-performance computing. So lithography, another case of us using supercomputers to actually help us build, to simulate and build better computers in the future. So that when we generate a mask, right, a mask to make a computer chip, the calculations in that, right, were far below the actual resolution that you would typically be able to focus. So you have to take into account all of the diffractive effects. And so lithography is extremely complicated, and it basically requires supercomputers to calculate the masks that you use to make computer chips. New materials is on the right hand is another example. So some other broader things are brain simulation. There's a large effort now in the world to simulate the human brain and to have some very broad goals of not only understanding how drugs interact with the brain, but also things about where is memory and how does it actually work. So they're already simulating, they have a whole sequence of rat to cat to monkey to human to try and get through all of these, and they've made pretty good progress already on understanding the rat. So we're getting there. The heart simulation, obviously a very important thing, and these are all things that we've already done, and I'm going to show you some of the things that we look at when we go to the future. But geosciences, earthquakes, there's been a lot of work. This is a traditional area for high-performance computing. Weather and climate, you probably know. The things that when you see forecasts of global warming and what it's going to be in 20 years, these are all things that result from supercomputers. So when we look forward and we say, well, so why can't we just do these with lots of small computers? There are a number of applications that really do require an enormous amount of computing to get to the next level. And so here's a brief sampling. So we have whole organ simulation. If you actually want to simulate a whole organ, it's an enormously complex object. Lithium air batteries. This one is extremely interesting. It turns out that the chemistry is extremely complex, but that it's pretty well accepted that there is about a factor of 10 out there to be had in terms of the energy efficiencies of batteries over what we have today if we can get this right. And this has become a huge computational effort, and it's believed that you really need on the order of an exascale of computing to sort out this. There's the smart grid, nuclear energy, and then the whole engine design. To simulate all of the turbulence in a real engine design is an extremely complex problem. Carbon is also trying to save carbon as it leaks out and trying to model all of that. These problems get very big and require enormous computing very quickly. So tumor modeling is another example. So let me talk a little bit about some of the trends in the market, because I think this is an important piece of this. So just so this is a AAAS slide that shows that the U.S. market, and the scale here that's important is that the overall R&D in the world is about $1 trillion in R&D. And so the reason I'm taking you through this is, and here's the profile for the U.S., and you can see that a lot of this is actually funded by private industry. The government's still a big part of this, but you can see the private industry contribution is getting larger and larger over time. But the HPC, the current HPC component in this IDC chart, you can see here in the middle column, the 2010-2011, it's about $10 billion. There's about another $10 billion in revenue that comes through HPC. This is sort of the hardware aspect, but there's also the software and services, which account for about another $10 billion. So overall, it's about $20 billion. But $20 billion out of $1 trillion is a very small number. And here you can see the trend in computing. So this is the important point to see here, is that these curves, in terms of both the sustained performance as well as the peak performance of systems, are really going very close to 2x a year. So we're on this exponential curve where the performance is literally doubling just about every year. Well, right now, if this starts to open up all types of new simulations that can be applied, since the R&D budget really is so large worldwide, there really is a huge opportunity for HPC as this doubling continues. So in 10 years, systems really will be 1,000 times cheaper. You shouldn't think of this as peak performance. Think of it as cost performance, which is a very similar curve, because the amount of cost of these systems is only growing very slowly. So that in net means that the cost efficiency of computing is doubling almost every year as well. And that's the important point here, is as computing gets cheaper, if computing in 10 years, it really is 1,000 times cheaper, which from what we can see will be the case, it will look like there will be many of these things which are currently done experimentally that can start to be done through simulations. So this represents an enormous opportunity for high-performance computing. So let me talk a little bit about some of the challenges when we look to the future. So I'm going to take you into perhaps a little bit more technical direction here. So as I said, we're trying to go 1,000 times more. So we currently have systems on the order of 10 petaflops, which is about 100 racks. And we look at in 2019, this will be about a third of a rack for something of a similar performance. The harder things here are, not only the 1,000x overall performance, but the energy efficiency has to be over 100 times more energy efficient than that system, and with a footprint of about 2%. So what are the challenges that we're trying to face? There's really three different dimensions here. One is that cost performance, where over a 20 petaflop system in the 2011-12 timeframe, which we know how to do, and we're there obviously, but we need a 50x improvement in that. On the lower right, we need that 20x improvement over that same design point for the performance per watt, and we need, from a reliability perspective, about 50x improvement. So all of these improvements come when silicon technology, we've got 3 or 4 generations. So it's not all coming from the silicon. And also, when you look at silicon, right, every generation, it's true we can get about twice as many things on the silicon, twice as many circuits, but a lot of the power is associated with the communication across the chip. And so a lot of that has to do with distances, and so it's a linear dimension. So in the end, all we get in terms of the reduction in linear dimensions is about 3 or 4x over that time. So we've got to improve that through architecture. The other thing that happens is because we only have 3 or 4 generations, we need much more silicon to actually achieve these performance. So this is a chart that shows you some of the power efficiencies of, this is sort of the current world's fastest and best power efficient machines. And what you find now is that the world's fastest machines tend to also be the world's most power efficient machines, simply because energy is already a big part of the cost and one of the real constraints in these large systems. So how do we approach 2x per year when these are actually the scaling terms? So when we look in the silicon, circuit density per year is only improving about 1.4x, and wiring, as I said, is a linear dimension, it's about 1.2, and the energy density improvement that we get from the technology is also about 1.2. The chip packaging is even slower, right? This is a very mature technology already, so the I/O densities that you get in a traditional package are only slowly improving, as does the electrical card wiring, number of layers. All the things that you would have in sort of conventional package are just not going to be able to stay with that 2x per year. So there's a lot of things that we need to do through an architecture to continue to ride this wave. And so what we're doing, so one of the things that we do is we're pushing more and more compute onto silicon, and the result of that is that the compute chips are getting faster and faster, but what do we do about the I/O? So one of the things that we have to invest in new I/O technologies, and I'll take you through a little bit of what we're doing there. So one of the key things is, as I said, power is distance. So we have to keep the distances short if we want to continue to reduce power. So even if we can put more and more on a chip, we have to contain the distances that we're actually moving data back and forth. But the net of this is that the optical boundary will continue to move in. And so let me talk for a moment about one of the questions. So as this factor of 2 hits us every year, well, we're not getting it through frequency. You can see that if you go and bought any commodity processor recently. They're really not much faster than they were 5 years ago. So we're not getting it through frequency. It's all coming through other forms of concurrency or parallelism. So you would worry that if we have to go a factor of 50 times more performance over where we are now, that you need to have 50 times more concurrency, and you have to exploit that in your program, 50 times more parallelism. And that is a huge challenge, and it is a real issue, and it's a big challenge for the whole community. This chart just shows possible ways of exploiting that concurrency through actually threading your code and using that threading of the code to get the parallelism, so that from a user perspective, it's not quite so formidable. Another dimension here is reliability. So as we start to exceed the natural scaling of the silicon, as I showed, the silicon doesn't scale at the rate we want to keep these systems scaling. What happens is we have to use more silicon effectively. We certainly need to use more silicon for the actual compute part, because the number of floating point units, the number of integer units just has to increase because the frequency is not increasing. So there are different ways of dealing with this. And this becomes a big challenge for how we build systems, actually, because we've starting to use so much silicon that the rate of cosmic upsets starts to become a real risk that the failure rate and the rate at which we see wrong, basically you would generate wrong answers unless you have protection mechanisms, starts to become a problem. Well, we know how to deal with this, and there's a lot of engineering that's gone into this over the last 20, 30 years. Systems, we know how to build reliable systems, but they cost, it costs a little more money to do that, and it does mean that you have to design it that way from the beginning. So there are different approaches on how we can do this. We can either leave it to the hardware and the compiler to deal with it, so we can put that cost into the system from a fundamental perspective, or we can push that cost to the users or to middleware. And when we do that, it of course impacts a much broader community, and it's much more difficult. So what we're trying to do is to keep this at the top and still so that we can continue to build very efficient systems, but it does mean a holistic design from the beginning, that the whole system, including the fundamental properties of the processor, have to be built with the idea that this is going to be used in a system where there's 100,000 of these. So one of the key drivers when we look to exascale is the cost of the optics in the system. So when we look forward to exascale, this table shows you there's two in the table. The columns represent sort of different levels of investment in the structure, and then the rows represent the different topologies. So just to give you some orientation, so in an exascale system, in one machine that would be running at an exaflop, we would typically want on the order of an exabit per second of bandwidth to be supported overall in the system, right? So that's 100 petabytes per second of aggregate bandwidth. So now you can see why, and that's in a single system. So now you can see why these machines are sort of pushing the technology, and also not only from the way the technology is done, but also the cost of the technology, because the cost is such an important factor. You can see if we just use current technology on the right-hand column here, that we'd be in the billions of dollars of cost to get to these type of performance levels that we want. Even with silicon photonics, fully integrated silicon photonics in the left-hand column, we can get to maybe $60 million for one machine for the cost for that optics is about the scale that we think we can get to. The other point to mention here is the power. So for a 10 picojoules per bit, if we had 10 picojoules per bit, it would still be 20 megawatts of power in that 10 picojoules per bit. So that's way too high. We can't afford 10 picojoules per bit. It's got to be less than that. Because the whole budget for these machines is 20 megawatts. That's about the scale that we think the budgets are. So we have to drive the power down, we have to drive the cost down, which is one of the reasons you can see that HPC is really one of the key drivers and why we're investing a lot in this technology ourselves. So this is one of the areas we've been working on silicon photonics for some time, and we opened up some of the things that we've been doing late last year in terms of the silicon photonics, and you can see how this is so critical to us being able to reach the targets that we have, since these are such aggressive targets. So one of the key things here is, of course, to do this front end of the line integration for the silicon photonics, which allows us to do much higher density, allows us to transition to new technologies. And there's going to be more talks about this throughout the conference. So I just want to say one thing about memory. And so here's the historical memory price per bit. And I won't belabor this, but you can see it's not falling nearly at the rate of this factor of 2 per year that the compute is falling at. And this is just one of the forces that is really changing the way we do things. And so let me talk about how will optics play into these systems. So when we go back to how we built the original Blue Gene system, so we're now on our third system that's coming out in 2012. Well, in the first two systems, we didn't use optics. Even between racks, we didn't use optics. It wasn't cost effective. When we went to our 2012 system, we eventually had to go to optics between racks. From a cost perspective, it was similar, but what happened was we couldn't get the density anywhere near what we wanted to do. In supercomputing, density is very important because there's a surface to volume effect. The more density you can get, it helps cost in many ways. As we look to the 2018, we believe that, so in the 2015 timeframe, we believe that we'd probably be on the edge at that point of just still maintaining optics as when you go beyond some electrically interconnected grouping. But in the 2018, all the nodes will start to become connected with optics. Again, it's a density thing, and I'll show you in a moment here the numbers. So in 2021, we're at that next level where we've even broken out that in the chip we have fundamental problems, so optics is going to have to move in. So it's pretty clear that from our perspective that optics is playing a more and more important role as we go forward. By the way, on this, the systems, typically it's about 5 years from concept, from first thoughts to actually delivering systems. So it's a long road, but that means that, the 2015 system, we already have a pretty good idea what it looks like, and we have some thoughts on the 2018. So just from a numbers perspective, what kind of numbers do we have? So in 2012, we have looks to be pretty simple numbers from a number of pins needed. You can see that you only need 80 I/O pins to support the kind of network that you would want in 2012. The bidirectional bandwidth in terabytes per second, so it's only 20 gigabytes per second, and the memory bandwidth's 50 on that range, 50 to 100 and these are achievable numbers, and these are what we believe you'll be seeing in the 2012. But the 2015, now we have an order of magnitude bump. But because the I/O density is not increasing, we already have a problem at the memory bandwidth. We already have too many pins. If we had 800 pins for the I/O, you can see we'd need more for the memory. So it's already broke from a memory perspective, even at the 2015. So you'll see new technologies coming in to alleviate that. I'll talk to that in a moment. 2018, now we're at the 3 terabits for the memory, 1 terabyte, sorry, and 1 terabyte for the I/O. We're starting to get into a whole nother realm where we have 4,000 pins. This is too much to be able to pull off through conventional packaging. And then at the next step, we're in the sort of outrageous number range here where we need to start to look even further but obviously in the 18 and the 21, the only way we can achieve these numbers is with fully integrated silicon photonics. So in the 2015, what does the picture look like? So in the 2015, we see that we're going to have memory stacks. As I said, we already have a problem with connecting memory to compute. And with traditional memory and the way it's scaling, it won't be able to achieve the kind of performance levels that we want. So there will already be a new memory interface technology that allows us to get truly on the order of 2 orders of magnitude more bandwidth out of a single device than what we can do today. And that's sort of going to save us from a memory perspective. And we still believe that these can still be electrically connected onto some reasonably sized planar board, which then will carry optics off, whether those optical transceivers are photonics or not. It's still that you have that electrically interconnected nodes on the board. So basically, what happens here is we're starting that compute and that memory have to get much closer because we've already broken that I/O bottle problem. And so because that exists, because they've gotten closer, what happens is we go into a realm where we really have a system in a socket where the memory and the processor are in a single socket. It's not like today where you would have a DIMM and a processor. It's really that they're both together. So when we go to the next generation following that, it gets more extreme. Now we really need to move to sort of what's been sort of the holy grail of computer architecture for a while, which is a processor and memory, where you really have enough memory. Now, this requires that we have enough memory to really run real applications, right? One of the big limitations to processor and memory is if you have many different memory stacks, how do you put the processing there if you don't know which stack you need to talk to or memory device. So once you can have the entire memory that your processor needs in a stack, now you can actually fit it in a single stack. Again, distance is power, so this allows us to get the next level of integration, and this is where we believe we'll be going for the next step following that. And then also here you can see the photonics. So for us to get to the cost levels and the power levels, we'll also have a photonics layer in this single stack. So the system, really it's a system in a stack, if you like, is where we would go. Now, if I look at the power breakdown, one of the things that we see when we look at systems of the future is that where the power is depends very much on what you're doing. And what you see here is that on the left hand, when you're compute dominated, that the power is very much in the processor core, sort of in the traditional way, and not too much in the memory. But on the right hand pie chart there, you see that the power is really in the memory. And the key thing to notice here is that if you now have a truly power optimized system where you can actually have the right level of power management, you don't need to design a system for the worst case, which in the bar chart on the right would be the level 1 there. But you can save 30-35% power by having a properly managed system. One thing you might see here that's interesting is that the I/O power doesn't change so dramatically. And this is an important message, at least from a supercomputing perspective. One thing that I wanted to mention is that from a supercomputing perspective, the most important power number for communication is actually how much power it takes when it's not being used. It might seem a little counterintuitive, but the biggest problem for us in supercomputing is that the processor. The processor and the memory will always dominate the power. And because of that, if the network is using power, even when it's not used, that's the worst case power point. The case where you're actually communicating, you tend not to be processing so much. And so that case actually is not so bad. The actual power when you're communicating is not so bad because the compute drops so much. The compute power drops so much. So what you really want to focus on from a supercomputing perspective is having I/O from the optical links, which powers down on a very short time scale and can power back up. And we're only using power when it's being used. So the other thing is, in all of these things, it always comes down to cost. You could see how even the architecture that we look at for the future, I showed you the different topologies of the network. The topology of the systems that we choose for supercomputers in the future are actually determined by optics. Because the cost of optics is such a high fraction of the system cost, we really optimize it for cost based on how we can use optics. So that has to do with how wide the optical pipes are, how many of them we need, and so forth. But it's not just the parts cost, right? There's reliability, right? The system has to be fundamentally reliable. There's the testing. There's the failover. All of these things, though, in the end, get translated into cost, and we have to pick the optimal point on it. And so, and in the end, parts don't necessarily dominate the cost. These other things are also very expensive. One of the things that we see, as I showed you those future system pictures, you can see how as we start to change take the 2015 where you have memory in a socket, this is a very different design point. Now, how do we configure our system? You're used to buying system. You can say what memory to put in and so forth. So the idea of configurability is a huge challenge. It's more of a challenge for commodities than it is for supercomputers, but it still represents a real challenge. And the other comment I'd make here is that electrical packaging, we've really kind of pushed it to the limit. And even when we can get another 30-40% out of in terms of bits per second on a single differential trace, it usually comes at such a cost in either power or complexity, design rules that it impose on the cards that are carrying that it ends up being, it's a bit of a false promise, and it's gotten extremely complex to try and push things electrically beyond where they are today. And so, we're sort of, at least from our use in optics and supercomputers, while the packaging is complex, at least we're not yet at the same level of complexity as we are with electrical. And I think there's some lessons to be learned there. Really, simplicity really does pay dividends in the end from a reliability perspective. And the other point I'd make here is that reliability really has to be addressed at the system level. And so that's the processor, it's the network, it's all as from a holistic point of view. So let me try and conclude then. So the HPC is really growing at this exponential rate, and staying on that doubling every year curve has enormous benefits for all of us. If we can stay on that rate, we will be more productive in the way we can actually do R&D, and it really will open up new avenues and improve everyone's standard of living. So this is an extremely important thing to keep riding on that train. But you could see, for us to stay on this sort of runaway train of doubling every year, it's not business as usual in any sense. We're basically violating all the technology laws to get there. The technology is definitely not getting us a factor of 2 every year. So we have to continue to innovate on the architecture to get there. And one of the things that happens there is we're pulling in that where we have to go to optics. And so optics is really one of the key things that will allow us to continue to stay on this curve. So the other thing is this 3D packaging. I mentioned the stacks and the proximity and where that goes to. So as we start to approach this 2x per, well, we're already on the 2x per year, the concurrency to exploit the ability to exploit that is extremely difficult. And so we need to explore ways of writing programs that allow us to explore new forms of parallelism without having to put this onto the user. And this is one of the big challenges. Is once we solve the technical problems of how do we build these systems that are doubling every year, we have to find a way to use it. And it's really that usability. When I say there's going to be all these new applications that are going to start to flow into HPC because there's $1 trillion in R&D and there's only 20 billion in HPC, you can bet that all those new users who are going to find HPC attractive aren't going to be HPC experts, and so they're not going to be experts in parallel programming. So making these machines easy to use is very important. And so that's both a fundamental, how do we design the hardware, but it's also a software statement. Okay, thank you.